The unnatural light composition in contemporary displays has negative effects on vision too, not just on eye health, as discussed in the previous presentation. So in this one, I'll be briefly going through how it affects color vision, clear focus and its development, and visual performance, all of which are connected to digital eye strain and fatigue as well. So displays are optimized for quite simplistic color metrics, and over the years, with more technological options, their spectra have become narrower and narrower, so there are only spikes for red, green, and blue, but basically nothing else in the spectrum. And in the previous presentation, I discussed why this is bad for balanced physiology and eye health in general, but it also has negative visual effects, which are not captured by these simple usual metrics that are used to evaluate computer screens. And on the positive side, this property of narrower and narrower RGB spectra allows for a wider gamut, so more colors can be displayed, and higher saturation and color contrast, which is of course attractive at first sight. It creates very vivid colors, but then these unnaturally high saturation and unnaturally vivid colors have negative consequences in the long term, because there is an adaptation to them. So this high vividness becomes the new norm for the visual system, and then subsequently the real world is rendered more dull. And these adaptation effects can be quite long-lasting, so they should be avoided, particularly for children whose visual systems are still malleable. And this very same property also affects accommodation, so the setting of the power of the lens for clear focus. The way it works, or the reason behind that, is the following. Different wavelengths are focused at different distances, so shorter wavelengths are focused more towards the front of the eye, and this is called chromatic aberration, which provides important cues of depth for the visual system. Now, in natural light, because all frequencies of light are always present in various proportions, when the focus of the lens is at least more or less correct, then some part of the spectrum will always be in perfect focus. And that's not the case with narrowband RGB stimuli, which pose an unnatural challenge to the visual system, and there are only two options to solve this challenge. One is that the lens is focused on one of the three components, so either red, green, or blue, but then the other two will be quite out of focus. Or it can focus somewhere between, but then all three will be somewhat blurry. And this challenge is greater with narrowband blue light, partially because, as you can see in the right-hand side image, chromatic aberration is not a linear function, so there's a larger correction necessary for shorter wavelengths. And another part of the reason is that S-cones, the receptors which are responsible for detecting short wavelength light, are basically absent in the fovea, the part of the retina where detailed vision takes place. And studies in this field have shown that in general we compensate well enough for this problem so that it's not noticeable, but it puts still an extra accommodative demand on the visual system. And in more challenging situations, like in dynamic viewing situations, this also shows up as lower visual performance. So when you have to look up from the display and focus in the real world at something farther away, and then look back at the display, then this refocusing will be slower and less precise with an RGB display spectrum, as opposed to with a real object in full spectrum natural light. And they also show that there is overcompensation for wavelengths below 430 nanometers, and again, this is connected to the fact that blue light is particularly challenging in this respect. And the phenomenon and this is the phenomenon also behind the temporary myopia that many people experience with prolonged display viewing. And there is some indication that this may contribute to real myopia as well. So there might be some translation from this short-term effect to long-term short-sightedness as well. But what we know even more clearly is that childhood development of good focus relies heavily on the presence of the whole spectrum, and especially the balance between the two ends of the spectrum, again because that's where chromatic aberration is the largest, the difference in focal length is the largest. And so when either end of the spectrum is missing, or when the balance is upset, then the longitudinal growth of the eyeball doesn't stop when it should. And so it keeps growing and becomes too long, resulting in myopia of the worst type. So here the issue is structural. The eyeball becomes longer than it was meant to be, and so that also raises the likelihood of other eye problems further down the line. And as mentioned before, in our indoor light environments, we are usually lacking the long end of the spectrum because it's not contained in the light of computer screens or most electric light sources, and it's also largely filtered out by modern window glazing. And the short end of the spectrum is also quite unnatural in its composition. And on the flip side of that, spending more time outdoors is protective against myopia. So compare this to the fact that in the past years we have seen remarkable progress in slowing down or even reversing myopia in children with lasting effects by using red light therapy. And these therapeutic protocols rely on brief but intense presentation of deep red light, basically supplementing what is missing from our indoor light environment, or at least that's one explanation of its effect. And that is, of course, for practical reasons. The session cannot be too long. However, because of the necessary high intensity with these protocols, there have also been several injuries. And so basically, providing the same dose and even much larger dosage of deep red light can be done far more safely and naturally, as it happens also outdoor in daylight, when these frequencies are always contained in natural light, and so they are presented at a low intensity but over a long duration. And so in natural circumstances, daylight always provides this greater dose in a safe manner. And in addition to the aforementioned spectral differences between RGB regular displays and natural light, there's one more difference which is very significant for both vision and health in general, including neurological health, and that is flicker. And it's a large topic which would definitely deserve its own presentation. But so just very briefly going through some common misconceptions about flicker, which is a rapid periodic change in the intensity of the light or in the color of the light. But I won't even go into that. It's a more niche topic, but unfortunately also quite relevant to displays. Anyway, this periodic change cannot be detected generally when we just look into the light source or at the display when its frequency is above 60 to 100 Hz. However, during fast eye movements called saccades, this flicker shows up as a repetitive pattern of the stimulus on the retina because the eye moves quite quickly, and so instead of a continuous blur, as the light is flashing, it creates repetitions of the same image. And that is very confusing for the visual system because it doesn't know which of these many images is the real one. So basically it misses where the saccade should land, eye movements become imprecise, and that slows down reading and decreases our visual efficiency and increases fatigue. And reading itself is already a very similar challenge for the visual system because of all the repetitive vertical structures in fonts which then overlap. And so adding the two problems together, reading, which is already a challenge for the visual system of this kind, and flicker, which then exacerbates this problem, is then particularly difficult to resolve. And that is what many people can feel, either as a visual problem or as difficulty in reading, or just through fatigue and neurological problems, headaches, etc. And so understanding this mechanism shows that the most disturbing frequency is where the spatial sensitivity for patterns is highest, and that is around 3 cycles per degree. Again, how these repetitive images on the retina are drawn is going to determine how likely it is that they will be disturbing vision. And so because of this mechanism, we can see that the problem, or how problematic flicker is, depends on the frequency, but not only on the frequency, it also depends on the velocity of eye movements, which varies quite a bit also between individuals. So people who have faster eye movements will experience more problems with flicker. And it of course also depends on the contrast and the size of the stimulus. And so with faster saccades, the worst flicker can even be 1,000 hertz or higher. So we cannot say that something is flicker free because it's above a frequency. And these are certainly frequencies which are well above the fusion threshold. So generally what is considered easily visible without any eye movements as well, again, ending somewhere around 60 to 100 hertz. And so there are many claims about flicker free displays or lights because they are above some frequency, and these claims are highly misleading and incorrect, whether or not on purpose. And for example, because of this same mechanism, 300 hertz is not necessarily better than 100. In fact, in many cases, it can be worse. And also, there is no magical number, a highest ceiling above which flicker doesn't matter. The more we look into it, the higher numbers show up in the literature where people can reliably detect flicker. The highest so far is around 15 kilohertz, so way higher than what most people consider really high frequency where it can be claimed to be flicker free. And even when flicker is not perceptible in any way, the nervous system resonates with the frequency of this rapid turning on and off of the light. And that contributes to headaches and fatigue, and again, reading problems linked to a disruption of eye movement planning. So in short, flicker should always be considered problematic, and the true solution is only to eliminate it. So thank you so much for watching. In the next part, Liliana is going to tie all of this to how we are eliminating the root cause of these problems by bringing sunlight into a computer screen.